Alright, so in this video I'm going to be explaining another important article with the title Domain Generalization via Multi-Domain Discriminant Analysis. This paper in 2019. Domain generalization aims to incorporate knowledge from multiple source domains into a single model that could generalize well on unseen target domains. This problem is ubiquitous in practice since the distributions of the target data may rarely be identical to those of the source data. In this paper, we propose multi-domain discriminant analysis to address domain generalization of classification tasks in general situations. Multi-domain discriminant analysis learns a domain invariant feature transformation that aims to achieve appealing properties, including a minimal divergence among domains within each class, a maximal separability among classes, and overall maximal compactness of all classes. So you see the illustration of the domain generalization on Office and Caltech dataset. That one is given the source domain, webcam, Caltech, DSLR, and aims to train a classifier that generalizes well on target domain Amazon, which is of course unavailable in training. So you're familiar with kernel mean embedding. I have a playlist for reproducing kernel Hilbert space. So let's focus on problem definition. First, they assume that each sample is assumed to be generated in two separate steps. A domain P sub S is sampled from beta in the product space where S is a domain index. N to the S independent and identically distributed IID drawn from each source. And M, we have M domains. So our aim is to incorporate the knowledge of the domains into a model which could generalize well on previously unseen domain. And so there are some regularization measures, average domain discrepancy, or another way is average class discrepancy. And we can incorporate instance level information. Both average domain discrepancy and average class discrepancy are defined based on the kernel mean embedding of class in conditional distributions. So by simultaneously minimizing psi add and maximizing psi ACD, one would make class conditional kernel mean embedding within each class close and the dose of different class distances in H. However, certain subtle information such as compactness of distribution is not captured in them. As a result, although all mean embeddings satisfy the desired condition, there may still be a high chance of misclassification for some instances. This is the multi-domain between the class scatter. And n sub j is just the total number of instances in class j. And n sub j, so we get this mean representation of the entire set. And then we can also measure the multi-domain within class scatter. But X here denotes the feature vector of the ith instance. And inside ith instance of the class J in domain S. So that's why we have three summations over classes, over domain, over samples. So we have feature transformation. Our method resorts to finding a suitable transformation from reproducing kernel Hilbert space to a q-dimensional transform space. So we go from the Hilbert space to the RQ, which is easier to think about. According to the property of norm in reproducing kernel Hilbert space, psi-act can be equivalently computed by the trace of this matrix. And G is given by this one. So in practice, one exploits a finite number of instances from M-source domains to estimate the transform measures. Since all measures depends on mu sub j and u sub j, the estimation of measures reduces to the estimations of mu sub j and u sub j using the source data. So we have this empirical estimation, and it requires the probability of your S given Y. We can use Bayes' rule, so it's very easy to use Bayes. And then the empirical estimation of mean representation of class J in reproducing kernel Hilbert space is this one. By substituting the empirical class and the empirical mean, these matrices can be estimated from M observed sample sets using the kernel trick. But because they are working on trace, so they have a problem, optimization problem, some technical problem. It can be seen, so we only measure in the unify measures introduced in the previous section and solve B like this problem. It can be seen that through maximizing the numerator, the objective preserves the separability among different classes. Though minimizing the denominator of this is like this. Tries to find a domain invariant transformation, which improves the overall compactness of distributions of all classes, and make the class conditional distributions of the same class as close as possible. So by substituting the transform average domain discrepancy, class average class discrepancy, multi-domain between class scatter, and multi-domain within scatter, and we just use this for regularization. Then we can just we transformed our optimization problem to this one, which is easier because it is invariant to rescaling of B. Rewriting 16 as a constraint optimization problem and setting the derivative of its Lagrangian to 0. So we have a generalized, I have a video about generalized eigenvalue problem, so we can quickly solve this problem. So these are the inputs, but the output is the optimal projection B. Then the transform feature of the target domain are given like this. The rest of that is just theoretical things for upper bounds on the empirical measures.